Okay, now picking up exactly where I left off, we suppose that I want to make Excel do this t-statistic for me and just tell me whether I'm going to reject or fail to reject a null hypothesis. Well, I can kind of do that. Excel doesn't have a function built in that will do exactly the same step-by-step everything I just did here, but it will help you um, sort of cut to the end of the story. And most of the data analytical outputs in the data analysis tool pack are going to be packaged in this same sort of framework. So in this video, we're going to do that and then talk about two important steps that we should probably add to the story here. One is one-sided t-statistics. If I only care about one tail up here, because I only care about whether t is large, meaning I only care if x bar is above or below a certain value. And this is a good example to do that because perhaps I don't care whether the stock is not growing. I care whether it is strictly increasing or perhaps it's zero or decreasing. I would just add a little inequality to the null hypothesis over here, and then I've got a bit of a change. So there's that. We also need to talk about the t-distribution instead of the normal distribution, which is what we've been working with here all along. Now, the t-distribution I've mentioned in other videos is going to have fatter tails than a normal distribution, so we're going to wind up with a slightly different story if we use the t-distribution to construct p-values, which we are also going to see in this video. All right, well, that's great. Let's jump to Excel and try to ask Excel kindly to do our work for us. And I'm going to look at my returns that I've calculated here, and I'm going to look at the data analysis tool pack. The options that I've got here do include a lot of different things: ANOVA, two factors, descriptive statistics. Down at the bottom, t-tests. I've got t-tests and a z-test, which is interesting, for two samples. Now, typically, we will have a sample of data and another sample of data that we want to compare to each other. That's a very common thing to have in business and use what we would call ANOVA. We saw a two-sample test previously in the difference of means tests between school districts in California that had a large student-to-teacher ratio and school districts in California that had a small student-to-teacher ratio. I'm going to use one of these tools to cobble together the very, very simple t-statistic that I just did in this example with Tesla stock. The one I'm going to use is here, two-sample assuming unequal variances. Looking at the others, you'll see there is a t-test for two samples assuming equal variances. If you have two different sets of data that you want to compare the average and test whether the average is the same, and you truly believe that they should have the same variance, there is an option to do that, which comes with a different formula. The formula for unequal variance, which is the one we saw in the slides previously, happens to collapse to the regular t-statistic formula if I do something a little bit cute. So what I'm going to do is, it's already set up for the variable ranges that I'm going to use because I've done this before, and it's already set up for the hypothesized mean difference. Okay, all right, I understand that this test will require one set of variables, another set of variables, and then something about how different I think they should be. And look, I can even specify alpha here, which is the probability of rejecting the test and being incorrect. It's the probability of what we call type 1 error. This is also called the level of significance, and it's also 1 minus the level of confidence. When I say that I'm 95% confident, I mean that there's maybe a 5% chance that I would accidentally reject the null hypothesis even when the null hypothesis is true. You say, well, if mu is here, I shouldn't see x bar this far out, except maybe 5% of the time. So 5% of the time when the null hypothesis is true, I will accidentally reject it. Depending on how bad that is for your business use case, you may want to reduce that number and be 99 or 99.9% confident. But that's this. That's what alpha is here, and we saw that previously as well. All right, it does require two sets of data. So what I'm going to do is put that away. I'm going to come up here. I'm going to insert a column, and I'm going to insert a column of zeros because I don't want to test these returns against another set of returns, which perhaps could be interesting if I'm comparing two stocks. But I'm going to test these returns against a column of all zeros. Data analysis, unequal variances, variable 1. I'm going to select the first 50 observations from row 3 all the way down to row 52 of the Tesla stock day-over-day percentage returns, which we just tested whether that was 0 on average. And I will collect the first 50 observations of these zeros in the other column. This is a bit of a hack. So I'm making Excel do a t-test for a single variable against a hypothesized value by giving it a column of zeros, which have no variance. So it is, in fact, a constant. And the hypothesized mean difference between these percentage returns and the zeros that I see in the next column should be 0. So it will test the null hypothesis that the average of these data here is equal to the average of these data here, which is exactly the constant 0. What am I testing? This right here. Interestingly, Excel does not care as far as putting it into this function whether your null hypothesis is that mu is equal to 0 or whether your null hypothesis in the one-sided case is that mu is less than or equal to 0. You'll notice I can do one-sided null hypotheses as long as equality is here. Equality always goes in the null. I could compose a alternative hypothesis there where I say alternative. Well, it's the logical complement to whatever my null hypothesis was, so I'll say mu is not less than or equal to, strictly greater than 0. Now I'm testing whether the stock has positive returns. Strictly positive, not just different from 0. That's a little bit improved in some ways, and if I reject the null hypothesis in favor of the alternative, then I've found the thing that would be really good. This stock has strictly positive returns at the 95% level of confidence. I've already seen the t-statistic, so I don't think I'm going to find that. But it's worth mentioning that that's one of our options. In that case, the rejection region for the picture, right? So if I say here is perhaps the rainbow is not the best choice for a horizontal axis. If I say here's mu, what is the set of x bars that would allow me to reject this null hypothesis? It's going to have to be things that are actually, let's say this is 1, 2, 3 standard errors above and below. I'm going to need to see things, if it's 1.96 or if it's 2.58 or whatever the critical value is. Let's say this is your magical critical value. I want this shaded in region here to be alpha, the probability that I accidentally reject the null hypothesis. And this picture is very different from the other one we had, where there was an alpha over 2 on the right and an alpha over 2 on the left. So in the two-sided case, let me draw an identical picture. Here's what we were doing before. Okay, so 1, 2, and we can put the center of the distribution back in up there. In the two-sided case, I've got something like alpha over 2 and alpha over 2. Alpha over 2. Because I could reject on either side. If you're wondering, wait, what is the difference between these pictures? The shaded in region is supposed to add up to the probability of accidentally rejecting the null hypothesis and being wrong, which you want to control for. Depending on whether this is a one-sided or two-sided hypothesis test, you'll put all of that on one side in the one-sided case, or you'll split it up so it's on the right and the left in the two-sided case. We were doing this before. I'm making a point that there is a slight revision in the storytelling if we do a one-sided hypothesis test. So good comparison, nice picture to be able to draw if you're good at practicing the art skills that we do in a data analytics or statistical class. All right, well, we'll see this pop up here in a second. Back to Excel. I feed Excel my daily returns, percentage returns for Tesla stock, and I feed Excel a column of zeros with 0 variance, which forces this thing to test the average returns against a constant. And I say alpha 0.05, sure, will be 95% confidence. I only want a 5% chance of accidentally rejecting the null hypothesis if the null hypothesis was true. That's this alpha. It's the same as this the area of this range where I accidentally reject the null hypothesis because I got an x bar. Purely by chance, I got an x bar that was much larger than my hypothesized value mu, and it works the same in reverse if you swap x bar and mu, right? The logic is the same. Okay. Okay, interesting, thank you. Back to Excel. I'm going to hit the button and do the test. I send it. Excel gives me a magical set of numbers here. So it has returned a t-test for 2 samples. I've really only got 1 sample because I fed it a silly fake sample here. Variable 2 has mean 0 and variance 0, and I'm hypothesizing that the difference between variable 1 and variable 2 is 0. In other words, I'm hypothesizing that the true average of variable 1 is 0. This formula, because I've stuck in those extra zeros, collapses to the simple t-statistic formula that we have right here. And if you want to know the formula for the difference in 2 means, it's the one that we saw in some slides much prior to this. All right, so I've got my average here. I've got my variance here, which is not the standard deviation or the standard error, but I recognize the average as the same thing that I used to create a t-statistic in the previous example. I see that I have 50 observations, which is true for both variables because I happen to have chosen 50 observations for both variables. I've got a hypothesized mean. I have degrees of freedom, which is very important in a small sample. So we're going to have more to say about that. And I've got a t-statistic that I recognize as being exactly the same number that I cooked up myself when I did it from scratch using the mean and the standard error. Okay, so it does work. Now what does it give us? It gives us a critical value for a one-tailed test and a p-value for a one-tailed test. It gives us a critical value for a two-tailed test and a p-value for a two-tailed test. The critical value here is what t-statistic you need to see in order to reject the null hypothesis. And if you're thinking to yourself that should be 1.96, right? You are correct. Well, 1.96 follows the normal distribution, and what Excel has done here is actually a bit more sophisticated. Let's explain. The normal distribution story is precisely this, and we'll stick with the two-sided story for now, all right? So I'll draw a normal distribution one more time. Sometimes it's good, sometimes it could be better. Fair enough. And here's your average. Here's 1, 2, 1, 2, 2. Standard errors above and below. It's the same picture as always. And there's some story about, okay, I want 5% of probability to be left in the tail. I only want to be wrong 5% of the time. So 1.96 is the magical number there. Okay, this is 1.96. This is negative 1.96. And because I'm wrong 5% of the time, half of that is on each side. This is 2.5%. Chance of seeing a number way up there, seeing a t-statistic greater than 1.96. And there's a 2.5% chance of seeing a t-statistic less than negative 1.96. So these should be rare if the null hypothesis is true. And you should only accidentally reject a very small amount of the time. Of course, these numbers will occur much more frequently if the null hypothesis is false, which is the idea. The normal distribution is based on our central limit theorem conversation, which we don't dig into in this class, but I mentioned it previously. In a large sample, this shape is actually going to tell you how the mean behaves relative to its population counterpart, the sample versus population. Normal distribution, z-score shape, z-score table that we looked at, it all works. In a small sample, there's one funny thing about the t-statistic which contributes to this story. The t-statistic, you will recall, is x bar minus whatever value you hypothesized, which we'll call mu naught, and I divide it by the standard error of x bar. Standard error comes from the standard deviation. Well, standard deviation, you'll remember there's this n minus 1 in the formula for the variance, and it's always positive. It has its own distribution, which is a bit skew, which is to say it's a lot skew. The standard deviation in a small sample tends to be too small, and in a larger sample that's not a problem, but it tends to be too small or occasionally very, very, very too big. It has a distribution sort of like, here's 0, like this. Always positive and with a long right tail. Interesting, but what that means is this thing down here in the denominator is sometimes going to be too big, but often going to be too small if your sample is small. Okay, all right. Well, so how does it affect decision making? It affects decision making in the sense that in a small sample, the t-statistic coming out of this entire formula doesn't look quite normal. It has fatter tails. So I've tried to draw this so that it's a little bit shorter in the middle, and a little bit taller out in the tails. If I find the critical values such that there's only 2.5% of probability left in this new shape that's a bit too fat out there in the tails, you'll notice, well, 2.5%, it's supposed to be about the same amount of area. I've got to go out a little bit further to find those critical values. So instead of 1.96, I might have a special value like, say, negative 2. Hey, 2.009. I'll call it 2.01. And over here on the right, that should be 2.01 for that magical critical value, the cutoff value there. And you say, well, 1.96 was so easy to remember. I want to use 1.96 all the time, and it's a good thing to keep that in mind. We did notice previously that there may be some utility to rounding that number up to something like 2 and having a bit more confidence or a bit extra buffer, if you like that idea. In a small sample, in fact, you may want more than just rounding it up to 2. In this case, the critical values are 2.01. I'll show you the table that this comes from because the shape of the t-distribution and how fat those tails are depends on the sample size, and in particular, it depends on degrees of freedom, which is exactly n minus k. K is how many parameters you estimated in order to calculate the standard error that you're looking at. So n minus k. K, parameters? How many parameters did we estimate here? Well, this standard error is the square root of the standard deviation, which only has the sum of all the xi minus x bar in it. So the only thing we had to calculate was x bar. K is 1 here. All right. In this case, it's just 50 observations minus 1 because we calculated x bar. Fair enough. And there's a little bit of a variation in how degrees of freedom are used, but you'll notice that the formula for the variance has n minus 1 in the denominator. And that's what we used to come up with the standard deviation in the first place. So n minus 1 is degrees of freedom here. And yes, it is. Look, Excel is even reminding us this is going to be based on a t-distribution with 49 degrees of freedom. It looks like a normal distribution with slightly modified critical values. Over here, I've got a table. This is a t-distribution table. It's quite a very handy table. Quite and very. See, I said 2 different words to emphasize how handy this thing is. Very conveniently put together. I like to start all the way down at the bottom because you can start with z. A t-distribution with infinite degrees of freedom is just a normal distribution. In a large sample, the normal distribution was the right thing to do in the first place, like we said. So all the way down at the bottom, if I want to be 95% confident and I'm working with a normal distribution in the z-score tables, the 95% confidence critical value for building a confidence interval or doing a t-test is that magical number we all remember, 1.96. There it is. But watch what happens as I move up that column, staying 95% confident. If I back off a little bit and say, what if I only have 1,000 observations? 1.962. What if I only have 100 observations? 1.96, oh, 1.984. 1990, 2000, 2021, 2042, 2045. These look like dates, but as the number of degrees of freedom gets smaller, as my sample gets smaller, the tails are going to be a little bit fatter. And so we have this nice way of compensating for small samples in order to make sure that our statistical decision making, when I say I'm 95% confident, it stays 95% confident even if my sample size is small. I have to be a little bit extra careful there. How much extra careful? Well, 1.96 could become as large as actually enormous in a very, very small sample. So you're never probably going to use less than, say, 10 observations. But here is an example, 2.28 for 10 degrees of freedom. Of course, 10 observations would actually be 9 degrees of freedom here, and I'd have 2.26. Notice up at the top, 95% confidence corresponds to 2.5% in each tail. So 2 tails, 5% error, but only 2.5% in each tail. When I'm talking about a one-sided test, like is the stock return strictly positive versus 0 or negative in the null hypothesis, then for 95% confidence, I could use the other column. And one tail would have a 5% chance. So I would say I would only find strictly positive returns by accident 5% of the time. That would be the preferred way to do it. And conveniently, it's only one column over. So in the z-score case, I don't use 1.96, I use 1.645. In fact, that's in my picture here. So this is 1.96. This was for one-sided, this is perhaps 1.645. Not quite as far to the right because all of the 5% is there. Instead of 2.5 alpha over 2, it's 5% for the full alpha. That's what that is. And let's have a look. All right, so 50 degrees of freedom, 49 degrees of freedom. Here we go, 95% confident. I'm looking for a number somewhere between the 60 degrees of freedom and the 40 degrees of freedom. So I've got 2.0 for 60 degrees of freedom, and I've got 2.02 for 40 degrees of freedom here. All right, well, 2.01 sounds like the right number, and Excel is kind enough to do that for us. So, what did Excel come up with? Critical value for two-tailed test, 2.009 with 49 degrees of freedom. If I pop back to the table, okay, so what would it be for a one-sided test? It would be somewhere between 40 and 60, so I've got a 1.684 for 40 degrees of freedom and a 1.671 for 60 degrees of freedom. The magical number I'm looking for in order to reject my hypothesis is 49 degrees of freedom, 1.67655, and you see that Excel has this built in where it will generate those numbers very precisely. So fortunately, there's a formula for the shape of the t-distribution, and this can be done on the back end to tell us exactly the number we're looking for. All right, thank you, Excel. That was extremely convenient. So I know not only what my t-statistic is, how many standard errors my sample average is away from my hypothesized value, which I could calculate myself using these summary statistics on the other tab. Easy peasy. But Excel has given me the critical value, the nice compensated for a small sample size, extra good numbers that I need to look for in order to reject that. Now my 1.1892 is not going to be larger than 2.009. So I am not going to reject the null hypothesis. I fail to reject the null hypothesis that this sample average is 0. Once again, even in the one-sided case, if I change that up and say, I want to test whether mu is strictly greater than 0, using the null hypothesis that mu is less than or equal to 0. Again, equality always goes in the null. My alternative would be a nice thing to find, that this stock is actually going up. Do I find that? Well, I would need to see a number as large as 1.67655, and I only see 1.892. So no, I fail to reject the null hypothesis. Let's talk about the last two numbers here. The p-value, t is greater than or equal to t, two-tail, and the one-tailed version. This is your critical value done in reverse, and it is perhaps the most useful thing on this entire output. So the t-value, the p-value. One more thing. All right. Here's your picture. Zoop. You got something like a normal distribution. Good enough. No, I could do better. Fine. Forget 1.96. Just calculate the t-statistic, all right? So here's your average. Here's some plus minus 2. Here's your null hypothesis, I should say. You calculate whatever x bar is in terms of a t-statistic, and you say, well, the data that I got came in 1.2 standard errors above my null hypothesis. So the x bar that we actually observed gave us something like this, t equals 1.2, meaning that if mu is here, x bar is here, and then we relabel the axes to make everything 0, 1, 2, 3, 4. All right, so mu and x bar. How rare is a t-statistic of 1.2 really? If the null hypothesis is true, how often would I see a number like that? Because I want to make sure if the null hypothesis is true, I only reject numbers that I would see, say, 5% of the time or less. If the null hypothesis is true, I want to figure out what that cutoff is so that I only reject numbers that I see 1% of time or less. I want to control how often I accidentally reject the null hypothesis when it was in fact true. Type 1 error. Well, this is pretty simple. You've got a t-statistic of 1.2, and you know that you're working with a t-distribution that has 49 degrees of freedom. So shade in this area and tell me how much probability is there. If I had gone out to 1.96, there should be about 2.5% out there, right? How much probability is in this area on the t-distribution? Excel will tell us. And so here I have the one-tailed p-value, 12%. 12%. Excel is saying, even if the null hypothesis was true, you would see a t-statistic this large in that direction 12% of the time. So is this t-statistic really compelling? No, not at all. It looks exactly like the sort of thing that you would see if the null hypothesis is true. I'm not going to reject the null hypothesis. And if I want to turn this into a two-sided consideration, then I go to the other side and I say, you know, there's also a negative 1.2 over here. 1.2. And there's another 12% out there. So I go to Excel and I say, hey, what if I don't care about which direction it is? What if I want to know the probability of seeing a t-statistic with at least this absolute value? So it could be 1.2 or negative 1.2 or anything past those numbers. And Excel says, yeah, well, there's 12% chance of seeing a number that big on the right, and it's symmetric. So there's a 12% chance of seeing a number that big on the left. You've got about a 24% chance of seeing a number as large as 1.2 in general. It's actually as large as 1.189203925, right? So you've got a 24% chance of seeing numbers that big even when the null hypothesis is true. The logic is fairly straightforward at that point. If the null hypothesis is true, I'd see numbers like this all the time. So it's not enough to convince me that the null hypothesis is false. If, by contrast, I see a p-value less than 0.05, then I can reject at the 95% level of confidence. Or if I see a p-value less than 0.01, I can reject the null hypothesis at the 99% level of confidence. The story there is, if the null hypothesis was true, I would see this large t-statistic less than 1% of the time. Which makes it sound like that null hypothesis might not be true, because the data look remarkable if I believe the null hypothesis is true. That's why I start to think that the data and the null hypothesis do not go together. The data disagrees with the null hypothesis. But in this example, the data does not disagree with the null hypothesis at all. In the two-sided sense, I've got basically a 1 out of 4 chance of seeing a t-statistic this large if the null hypothesis is true, and I've got basically a 1 out of 8 chance of seeing a t-statistic this large in the one-sided test if the null hypothesis was true. So I failed to reject these null hypotheses. So thanks to Excel for giving me the nice t critical values instead of forcing me to remember 1.96 every time, or better yet, forcing me to go to the t table and say, how many observations do I have? It's not 1.96 I should look for. What's the good number? What's the really reliable number? Excel will do that for you and tell you the critical value here in these t-tests. And the p-value is going to be more or less a universal phenomenon. So look for p-values in relation to every other kind of test. When we test statistics like the slope coefficient in a regression line, or when we look at the f-statistic in a regression, which tells us the overall significance of the model, the idea is that the statistic, like the t-statistic here, would be a very small number if the null hypothesis was true. And if I see a very large number, I should see a very small p-value telling me the probability of seeing a number that large or larger is very, very low if the null hypothesis was true. Hence, we can reject the null hypothesis. When I see a t-statistic or some other sort of statistic and a standard error and a p-value, and I understand where they come from, my eyes are immediately drawn to the p-value, all right? So when you're trying to make a decision about whether you reject or fail to reject a null hypothesis in most of these cases, the magical one to look for is the p-value, and whatever your critical alpha is, your level of significance, if you're only willing to reject 5% of the time by accident, see whether the p-value is less than that, and you can make all of your decisions. Okay, I'll stop there, and I'll see you in the next one.